All right. Okay, so the recording has started. Perfect. Okay, so hello, everybody. Good evening. I'd like to thank everyone for joining us today, and I'd like to tell on behalf of the Ottawa chapter, I'm very thrilled that you're all here joining us for a very important topic. So PEO Climate Change Seminar today will be discussing one of the top topics that are going on globally. And I would like to introduce myself. My name is Sana Bushaben, and I'm the upcoming PEO Ottawa Chapter Chair as of March 9th. And as a lead sponsor for this event, we're thrilled to have you all here today. And just to give you a quick friendly reminder that this meeting will be recorded. I would also like to mention that the agenda for today real quickly. So we'll start up with the land acknowledgement right after I'm done talking. And then we'll go through the speaker intro questions. We'll have some poll questions coming up. And then we'll start the presentation. And then we'll go through the question and answer through Slido. So you'll have the link in the chat. So please refer to that link to put in all your questions. And then we'll do the concluding remarks. And at the end, we have a really fun networking event. So feel free to join us for that as well. So with that, I believe Maria has already posted the Slido link in the chat. So please use that. And I guess I've covered it all for now. So I'd like to welcome Christy, who will be giving the land acknowledgement. Thank you very much.
Hi, everyone. Thanks, Sana. I'm the chair of tonight's seminar. I'm so excited to have you here tonight to learn, share, and discuss our energy challenges and the potential solutions to climate change adaptation and mitigation. I would like to start my introduction for seminar by acknowledging that we are meeting on Aboriginal land that has been inhabited by Indigenous people from the beginning. I want to show my respect for their contributions and recognize the role to treaty making in what is now Ontario. Thousands of years after first treaties were signed, they are still relevant today. We are grateful for the opportunity to meet here, and we thank all the generations of people who have taken care of this land for thousands of years. Climate change is becoming a significant topic that we cannot avoid and should take action as soon as possible. This seminar is organized under a group of people at the PEO who care about climate change issues and really want to make a difference based on the multidisciplinary background. Our mission is to help engineers, practitioners, academics, decision makers, and regulatory committee members to set a vision and work on action plans, strategies for the climate change adaptation and mitigation in Ontario. This seminar will seek to look at the climate change impacting the energy situation from an engineer's perspective. Examples of potential solutions that engineers can engage to address climate change will be covered. Examples will include fuel and energy substitution, such as wind and solar replacing fossil fuels, electrification of vehicles, carbon capture and storage, and life cycle assessment. Audiences will take away with the answer of the question, what is the biggest energy challenge? And you will understand that there is no silver bullet leaving vast opportunity for engineers to make positive contributions to climate change mitigation and adaptation. Finally, I would like to express my appreciation for all co-sponsors who have been working hard together to make this event happen. Without your support and collaboration, we cannot go so far. Now, please welcome our co-sponsors, representatives, and members from PEO Ottawa Chapter, the lead chapter. Toastmaster TECS, Toastmaster SCORE, PEO York Chapter, PEO West Toronto Chapter, PEO East Toronto Chapter, PEO Scarborough Chapter, PEO London Chapter, Society of Women Engineers Ottawa, and IEEE Peterborough Chapter. Now I'll pass my torch to Marcel to introduce our guest speaker, Dr. Roydon Fraser.
Thank you, Christy. Good evening, everybody. Tonight I have the honor of introducing our speaker for the evening. Dr. Roydon Fraser is a professor in mechanical and mechatronics engineering at the University of Waterloo and has been a P.Eng since 1992. Dr. Fraser's research interests focus on energy systems, including alternative fuel, electrified vehicles, vehicle batteries, connected and autonomous vehicles, compressed air energy storage, geothermal energy storage and retrieval, carbon capture and storage, life cycle analysis, energy and exergy analysis, optimization of energy systems, thermoacoustics, and thermal remote sensing for precision agriculture and environmental monitoring. He has been a faculty advisor for the University of Waterloo Alternative Fuels team since its inception in 1996, resulting in the first student-designed and built U.S. Department of Energy's Advanced Vehicle Technical Competition's roadworthy hydrogen fuel cell vehicle. Among other recognitions, Dr. Fraser has received the Faculty of Engineering Teaching Award and the Engineering Society Teaching Award, along with the U.S. National Science Foundation Long-Term Faculty Advisor Award, and is a Fellow of Engineers Canada and a recipient of the PEO's Order of Honor. Please give a warm welcome to Dr. Roydon Fraser.
Thank you very much. All right, we'll
So
just
we
share.
have a question poll before presentations.
Oops.
Yes. So Dr. Ryan has some questions. So we will display the poll right now by noise. Yes.
Please let me know if you see I just displayed it. Let me know if it's visible for everybody.
Yeah, it
Perfect.
was.
Awesome. Thank you.
Please
Perfect.
please scroll your screen if you could not read the following question. We have 7 questions totally, and Committment will be the moderator of the questions and answers. Committment.
Yep, I will start reading the question number 1. What is the world's biggest energy challenge? 1, cost. 2, greenhouse gas emissions. 3, efficiency improvement. 4, emissions and pollution. 5, policy/decision making. 6, deforestation and species lost. 7, climate change. 8, technology. 9, other. What will be your answer? Question number 2. What is the cheapest form of large-scale electricity generation of today? 1, solar. 2, wind. 3, nuclear. 4, oil gas. 5, coal. 6, hydro. 7, geothermal. 8, woods. Question number 3.
Sana, I'm having difficulty actually making a selection, and I don't see selections being made. Am I missing something?
GMB is because co-hosting, we can't vote in the pool. It's only the participants.
Yeah.
Oh,
Sorry.
Sorry, Jim, you do have to write down your answers.
But I do see answers coming in, so it's looking good.
I'm on to question number 3. How many years of carbon capture storage is available in Ontario? Current best estimate. 1, 5 years. 2, 10 years. 3, 20 years. 4, 50 years. 5, 100+ years. Question number 4. Your goal is to minimize your radiation exposure. Which of the following would you drink? 1, crystal clear flowing BC spring water. 2, tap water. 3, water discharged from Pickering nuclear plant. 4, beer. 5, milk. 6, ocean water. Question number 5. Which of the following is a definition of sustainable development? 1, relating to or being a method of harvesting or using a resource so that the resource is not depleted or permanently damaged. 2, a set of 11 principles, including the principles of 1, ensuring appropriate valuation, appreciation, restoration of nature, and 2, no net loss of human capital or natural capital. 3, development that meets the needs of the present without compromising the ability of future generations to meet their own needs. 4, responsible management of building design, construction, and renovation, landscape practices, energy use, water, and waste management, emissions, transportation, procurement, within a framework of regulatory compliance and fiscal prudence. 5, the act of not being a glutton of the earth. 6, all of the above. Question number 6, what is the fastest energy conversion technology can go from scientific feasibility to significant electricity generation? Significant means producing at least 5% of the total electricity. 1, 10 years. 2, 20 years. 3, 30 years. 4, 40 years. 5, 50 years. Last question. How closely correlated are energy and the economy? Nearly 100% correlated. 2, productivity improvements change the relationship between energy and the economy. 3, efficiency improvements change the relationship between the energy and the economy. Not well correlated. Local climate and average transportation distances change correlation. 5, answer 2 and 3. That's all the questions we have. I'm just really curious about the true answers. I believe Dr. Roydon Fraser will give us the answers in his presentation. Thank you, everyone.
All right, I'll give it just 2 more minutes because a lot more of the answers are coming in now, and I'll pause the poll in a bit. Thank you.
Perfect. Thank you.
So when you're ready, I'll give the answers to all but question 1 before I start my presentation. So if you could just remind me of which question number, and I'll give you the answers, and people can compare to the results. I'm assuming everyone sees the results, right?
No, I think you might have to share that actually, if that's okay.
Yeah, I'll share it and just scroll through it and give the answer.
Perfect.
Okay, I'll do that.
Thank you. All right, so I'm going to end this and I'm going to share the results. So it's good. We have roughly 70 to 75% of the participants answering the questions. I'm going to share the results. So yeah, can you see the results?
Yes.
Yeah.
Okay.
So if you wish, I'll walk through the answers now.
Yeah.
Question 1, we are not going to answer because that's the purpose of the talk. The question is going to be, what's the biggest energy challenge? I'm going to give you some information. So we'll leave question 1 for now and come back to that. Question 2, what is the cheapest form? It's wind energy at the moment. It is by far the cheapest to install on land wind. A little more expensive if it's offshore. So that's just a quick answer there. In terms of the carbon capture and storage, the current estimate for Ontario is about 20 years. Now it's a crude estimate because there's a lot we don't understand, but that's a current best estimate for the amount of storage we have in Ontario for the emissions that we produce today of carbon dioxide. The one for the radiation risk, if you just use Curie's or becquerels, which is simply a radiation count, it's the nuclear discharge water. And that's just a simple indication that engineers have designed it extremely well, because if it wasn't as good as or better than tap water, people would be complaining. So we design our nuclear plants very well as engineers. So that's a good thing there. And the worst, your order is, it's less than 10 curies for nuclear discharge water. I'll give the other numbers in the presentation. So just wait for that. All right. The definition of sustainable development, all 5 are definitions that you will find. The one that's most commonly given is development that meets the needs of the present without sacrificing needs of future generation. That comes from the Brundtland Report from the UN. That's where you had all these countries agree to a definition, but the other ones are also widely used. In terms of how fast we can do a conversion technology, and I will present this in the presentation, it's 40 years. And that has implications for what we can actually achieve with our goal of trying to hit net zero. At least that's what we appeared. And the last question is how closely correlated energy in the economy? It's nearly 100%. So that's our answers. Are we going to start the presentation now, or?
Yeah.
Okay, I'll share my screen. And can you see the presentation? All right. So topic is engineer's situation, engineer's perspective for the climate change group here. Let's dive right into it. Now, if you're in my classroom, I would have asked you to stand up. So imagine you're standing up. You're on the line now, but imagine you're standing up. And I want you to sit down if you answer yes to any of the following questions. Do you drive an SUV, van, or truck? If you answered yes, imagine yourself sitting down. If you regularly exceed the speed limit by 10 kilometers an hour, sit down. If you own 2 or more cars, sit down. By the way, I would have sat down already. So this is not a test on your Puritan character here. I'll give you the punchline in a moment. If you use the drive-through, sit down. If you air condition your entire house continuously, have a seat. If you own more than one computer, have a seat. And finally, if you play games or watch videos on your smartphone, have a seat. Point is, all of these things require energy, and they're luxuries in many ways. And the point is, as Canadians, we love our access to energy. Okay? And the thing is, even when we're concerned about the environmental impacts are generally a secondary consideration, because all of those activities increase our energy consumption, increase the greenhouse gases, increase the impact on the environment. All right? As engineers, what we're going to try to do is create a future where you can have those luxuries, those standard of living benefits without the impact on the environment. So that's part of the challenge, right? Again, I'm going to ask you at the end, what is the biggest energy challenge we face? And I'm going to give you multiple ones to choose from as we go through this presentation. Now, as each Canadian, you consume about 1,300 or 13,500 watts. Now, that's a continuous. That's not energy, that's power. It's continuous. For each of you, that's the equivalent of having 4 Canadian Tire lawnmowers in your backyard, gas lawnmowers, running 24 hours a day, 7 days a week, 365 days a year, and you're filling them up with gasoline continuously. And if you have a family of 4, that's 16 lawnmowers. For an individual, that's the equivalent of 225 60-watt light bulbs, or over 1,200 LED light bulbs at 60 watts. That's what each of you, myself, everyone consumes in Canada. All right. So why the interest in energy? Why the interest? Well, why we're here, climate change. This is the climate change group. That's related to global warming. But we also have concerns related to smog and pollution. Acid rain, you may not hear a lot about it, but it's still a concern. Depleting non-renewable resources. This is not just about coal. This is also about the lithium that you have to actually make batteries and the like. There's a lot of non-renewables involved. Foreign dependency, right? The national energy strategy in the US is based upon energy security. We're going to focus on climate change and global warming. But with regard to global warming, I'm not going to talk about it. I'm going to take it as a given. Here's your classic hockey stick graph. We see the CO2 concentrations increasing in recent times. This graph shows a correlate with temperature. We're not going to debate this. You can go watch these movies. These movies are over 10 years old, but they got the basic arguments for and against global warming. But I do think the correct focus, and this is good here, is climate change. Because even if the global warming is small, it can have huge impacts on how the climate system is affected. All right, so that's going to be our focus. But what's people's, in general, real interest in energy? When does it come to the forefront? If you monitor the newspapers, when do people look up and say, did you hear about, how often have you said someone mentioned something about energy from the newspaper recently to you? Well, what you hear about is when the price of gas goes up. That all of a sudden becomes your local water cooler talk. So I'm going to focus on gasoline and vehicles. As you heard at the beginning, my expertise is on vehicles. I'm going to start with vehicles, and then I'll get to the bigger picture of engineering. But we'll get into some vehicle aspects here. And just some background that was mentioned. So it's over 25 years I've been supervising the alternative fuels team. We've designed, built, and tested 8 vehicles. The first roadworthy fuel cell vehicle in 2008, we drove it from Central Park in New York to the Capitol in Washington, for example. I just show one other vehicle there just to show a type we have. That's an E85, so an ethanol vehicle, 85% ethanol, 50% gasoline. The 50% gasoline is needed for Canada. In Brazil, they have 100% ethanol. We have a cold climate. You need, unfortunately, ethanol has a low vapor pressure. So you can't, it doesn't vaporize or ignite at low temperatures. So we need the 85. And that means it's a plug-in hybrid electric vehicle. It's a plug-in vehicle. So we design and build and test these types of vehicles. So that's a bit of my background. So I got a hydrogen car here and I have an E85, or let's even imagine it's a gasoline car. So I got a question for you. If you had a fuel leak or were in an accident, would you be safer or feel safer in a hydrogen powered car or in a gasoline powered car? Now, I know some of you probably, because this pops in my mind, Hindenburg comes to mind right away as soon as you say hydrogen. If that didn't happen to anyone here, I'd be extremely surprised. All right, so which one's safer? Well, let's take a look at, what happens when you have a fuel leak. Well, remember, hydrogen's lighter than air. And when you have a fuel leak, hydrogen tends to rise. And if you ignite it, it goes up. Gasoline, heavier than air. It sinks to underneath your car. In this particular experiment, 1 minute later of ignition, which car would you rather be in? So this is just to give you a little feel that there's things to, what may feel unsafe may be safer. What am I fearful of when I design cars? Not hydrogen, the batteries. The batteries scare me to no end, because all it takes is one ground fault that's not detected. I touch the vehicle and I'm dead in an accident. Okay, it's a scary thing with these high voltage batteries. Now, there's a lot of safety systems in there. I don't want you to be scared of your cars. They put a lot of interlocks in, but you really have to engineer them to be safe. Hydrogen, you give me a sensor and I hear a beep, I run away. That's literally, I'll run away and I'll wait and see when it's safe. So I'm going to talk about the automobile and the engineering to generate sort of some understanding of this energy situation. So this will be my focus initially. So let's take a brief history of the automobile. Initially, it was the luxury item before the 20s. It was a luxury item that the rich had to replace the horse and buggy. Then we had the Ford introduced mass production. And so the 20s and 30s, you started to see your upper middle class also owning vehicles. The war came along, the war effort took the industrial machinery of automotive and put it into the war effort. So cars didn't really advance much. But after the 40s, we entered the 50s and 60s, where the commercialization of the vehicle really took off, and styling and power and size became important to sell vehicles. It was such that my best friend's dad could see a vehicle 2 blocks away and could tell the year, model, and make of a car, right down to the year of a car from 2 blocks away. Try that today. I can be 2 cars away from mine and walk up to the wrong car and try to unlock it today, right? Styling was really important. Power was important. My dad owned a classic Oldsmobile 88 in classic family car. This is not a sports car or anything. 375 horsepower engine, right? If you got a 100 horsepower engine, 120 today, it's considered powerful. And of course, size was there. 1972, here comes the energy crisis, the oil embargo, boom. Fuel economy is really important. We got to conserve energy comes in. And then you have the 1960s where environmental consciousness came in, and it really emerged into this concentration on emissions with vehicles. So in 1979, catalytic converters became mandatory. So fuel economy emissions really became the key thing engineers worked on since the 80s, actually up until now. The next three major trends all were related to fuel economy and emissions. So alternative fuels was looking for lower emissions. Alcohols burn cooler, produce less NOx. Lightweighting, right? And going to unibody construction reduces the mass. You get more mileage out of a car if you reduce the mass. And the electrification we have today even advances that further. So that's all about fuel economy and emissions. So engineers have been working on fuel economy, emissions, and fuel economy you can think of as efficiency. All right, so let's take a look at the fuel economy that's been in new passenger cars. So this is the improvements engineers have made to the fleet of vehicles sold in the US, right? And I'll consider Canada to be similar, but this is US data. Notice it's continually been increasing. So they've been making progress. The new cars have all been improving in efficiency. That's good. We've been doing a good thing there, right? Improving the efficiency. All right. I'm going to focus on the years 1988 to 2004 to compare with a set of data in my next chart. If I take a look at my next chart, this chart is years on the x-axis. On the right axis, I'm showing the real world fuel economy. So this is the fuel economy that the fleet of vehicles driven in the US actually achieved. This is essentially the consumption divided by total miles driven, cars and trucks and light trucks and all that. And through the 1975 to 87, after the oil embargo, boom, we did a great, huge improvement. But what's this? Weren't we improving efficiency of new cars all along? But between 88 and 2004, we were actually getting less miles per gallon, lower efficiency overall from all our vehicles. What's going on here? Engine efficiency increased, and then it increases afterwards. Well, what was going on was we were selling more trucks than cars, and cars have a lower fuel economy rating. And in 2000, that's an important date. It's an easy one to remember. In 2000, trucks actually outsold cars. And by trucks, I mean vans, SUVs, of course, half tons. And you see lots of them on the road today. Just start looking around and count. See if you see more cars than trucks, you're going to see more trucks. And so, does this happen? Okay, well, that trend's already stopped, and we've got this great increasing trend now in efficiency, right? So at least this looks great. Things are going up, right? Let's take a look. Let's take a little further. What's going on? The bottom graph here is a repeat. Let me go back. This graph I'm showing here of the overall fuel economy is the bottom graph here, right? It goes up, goes down, goes up. The top graph is the total gasoline consumed, right? So the total gasoline relates to the total carbon dioxide emissions. And what you'll see is the fuel economy from 75 to about 87, 88 increased dramatically. But what happened to the total carbon dioxide emissions or fuel consumed? Approximately constant. That doesn't make sense. What's going on? Oh, and if we even look at the end point here where things look great, even when the fuel economy is increasing, say 2015 to 2020, gasoline consumption is increasing again. We had this little benefit from 2005 to 2012 or so, but now it's increasing again. So engineers have worked on efficiency. Our CO2 emissions are going up. What is going on here? Well, this is known as the energy paradox, or sorry, efficiency paradox, or Jevons paradox, right? It's common occurrence. I'll give some more examples of it. But before I do that, let's take a look at just fuel economy of all the vehicles out there in the fleet. Like, let's subdivide the fleet a little bit. And wow, doesn't a Tesla look super awesome? 119 miles per gallon. Yahoo! That's pretty good. Or is it? Is that really good? Looks pretty darn good. But they're claiming zero CO2 emissions. So that's really saying, I don't care where the electricity came from when I'm going to give that fuel economy number. So this is actually miles per gallon energy equivalent of electricity versus gas. And unfortunately, those are not the same thing. So in Ontario, if you plug your car, Tesla, into a charging port during the daytime, well, in Ontario, the way we meet additional demand is by natural gas. So effectively, driving in Ontario, if you plug your Tesla in during the daytime to charge, you're driving a natural gas car. So you can't get away from that. That's your source. So you're actually producing CO2 by driving a Tesla in Ontario. If you're in a province like New Brunswick, where they all use coal for electricity, you're producing more CO2 than driving a gasoline car if you drive a Tesla. So it's even worse. But let's just stick to Ontario here. So I'm going to do a comparison with the Prius. The Prius actually gets real world 45 miles per gallon for gasoline. And if I do the life cycle equivalent, that means I actually consider the upstream source of natural gas for the Tesla and gasoline for the Prius. So they are both fossil fuels emitting greenhouse gases. I get 130 to 140 miles per gallon equivalent, which that'll correlate to the CO2 emissions, these miles per gallons now. And the Prius looks awesome. The Prius is awesome, by the way. And the Tesla is excellent. There's no doubt about it. Okay. I'm just saying it's not exactly the full picture here, because on this diagram, Toyota has its Prius ranked down at 45. And you think the Tesla's way outperforming the Prius, but do they for CO2? No, they don't. So the key point here is electricity changes the story of what we've got. It changes how we calculate fuel economy. It changes the importance of how you drive in the drive cycles, changes the safety considerations, changes the environmental impacts, changes the comfort features actually we can have for more electrification. It changes the grid dynamics. I'll tell you, the electricity companies are not looking forward to having electric cars. You just wait for the expense of putting in new hydro lines in communities. And then you got to talk about heat pumps, but we'll talk about that in a moment. It's going to be an amazing cost to the system to electrify everything. And then change, and that's the economics, right? So I've just identified this Jevons paradox. So to make you aware that there are many cases where increases in efficiency, if that's your only thought as an engineer, it may not solve the problem because the impact can still increase, the consumption can still increase. And there are more cases of that, and I'll give some more examples. Another thing I just want to introduce very briefly to you, I'm not going to discuss it today unless there's questions, is this idea of window of viability. I call it the window of viability. I took the concept from ecology, where it's called the window of vitality. And essentially it says a system cannot survive if too inefficient. And you know this is essentially the survival of the fittest idea. If you're too inefficient, too slow, too weak, you're not going to survive. All right. But what's not realized is that, but also you cannot survive if you're too efficient. And you've heard things before their time. If they are before their time, they can be a problem. Do not try driving a fuel-injected car through the Sahara Desert. I'd much rather have a carbureted Volkswagen from the 1960s. It's going to get me across the Sahara Desert. Depends on the environment you're in. Too efficient is not necessarily better. Other examples of the Jevons paradox, house construction. Just go drive around the neighborhood from the 1940s and 50s. Average house size, 700, 800, maybe 1,000 square feet. Today, 2,000 plus square feet is probably the average house size. We get more efficient with our heating. We get more efficient with our insulation. We build larger homes. Net energy demand actually goes up. History of manufacturing, same thing. We get more efficient with our manufacturing. The products get cheaper. More people buy them. If there are enough people buy them, the energy demand actually goes up in their production, right? And that's what companies want. They want to grow. That creates more energy demand. What about paper versus electronic? Well, this is a slam dunk non-Jevons paradox, isn't it? Electronic documents, we know use a lot less. If I have this PowerPoint's using a lot less energy than the production of paper to produce this PowerPoint if I had paper for all the slides. That's known. But this electronic document is going to remain stored. It's going to be a parasitic load, for example, in data centers or on my computer. And what actually that means over time, the energy demand is going to go up to keep that historic data. And it can actually end up consuming. It's actually right now, it's about equal to the paper production. but there's no carbon storage. So it doesn't even have the advantage of carbon storage. The energy is the same, but no carbon storage. So things to be aware of outside of sort of just a cycle of efficiency. This is just a quick graph from the Canadian Institute of Climate Choice report. Great report. I recommend it as a read. This is the Canada's net zero future. What they did was something awesome. They looked at over 60 scenarios to reach net zero. Only thing I want you to focus on here, it's greenhouse gases plotted versus time here. Net zero, you get down to the 0 to 2050. Don't look at the details here. I just want to say they have scenarios. They have different scenarios. What I want to look at is sort of the range of the scenarios. I want to look at efficiency. So on the next graph, and they also produced this graph here, you can see efficiency there. And for us to reach net zero by any of their 60 plus scenarios, efficiency has to improve dramatically. But didn't I just introduce Jevons paradox? We can't just jump at efficiency. We have to know something more. Okay, and then the other major one is fuel switching. I'll come back to fuel switching. But on the efficiency one, how do we improve efficiency greatly? Well, one of the scenarios is heat pumps. We should be using heat pumps. I agree, they are a lot more efficient than gas furnaces. They run on electricity. Your electricity grids are not going to like that, but that's what they're going to want. If we're going to want them to be at the magnitude that they need to be by 2050, by around 2035, we're going to have rules of you're no longer allowed to put in gas furnaces. Or, and I'll make a special note here and I'll circle it, this yellow, or we need to have successful commercialization of early stage technologies for the gases. That has to do with collection of CO2 and sequestering and carbon storage. All right. Early technologies. So remember that when we come to talk about gases. Okay, so there's the efficiency side of things. So are we going to prohibit gas furnace sales? Are we going to go that far? And what's the impact on the electricity grid? Well, we are going to ban gas heaters in Vancouver. You're not allowed to put a gas heater in. They all have to be baseboard heating or heat pumps. You're no more, it had to be zero emissions. In Quebec, they haven't banned gas heaters, but oil furnaces are banned now in Quebec. So it's happening already. So that may be the future. Okay. But take a look at this. In BC, remember Vancouver's in BC. This is also in BC. They have rebates of $1,000 on furnaces and $8,000 on heat pumps. What this article is all about is that the furnace rebate is capturing the majority of people. 90% plus of people that are getting rebates are going for the furnace rebate. And few people are going for the heat pump because the heat pump is still very expensive. It's a cost decision. So here we have a situation of a rebate for a high efficiency furnace. So that's an efficiency improvement, but it's actually making things worse when it comes to the future where we have to replace with heat pumps. Okay, what about fuel switching? That was the other major way of reducing emissions. Well, if we take a look at the EPA and alternative fuels, here's the definitions. Everything in red here is a fossil fuel. These are officially alternative fuels. And in fact, a lot of Canada's achievements at reducing carbon dioxide emissions in Canada have been by introducing natural gas in place of coal or oil. So it's not that we've had these great improvements because we got away from fossil fuels. We simply replaced them with other fossil fuels, natural gas, right? So methanol is made from natural gas, right? Propane, it's considered an alternative fuels. Hydrogen, it does not come from electrolysis dominantly today. In fact, a lot of the sort of future thoughts about how Alberta may stay a strong economy is to get hydrogen from natural gas. Okay, and that would be considered to be gray or blue hydrogen. If you sequester it, it'd be blue hydrogen. If you don't, it's gray hydrogen. Right? Coal. Now, coal-derived fuels, synthetic gas. I want you to remember synthetic gas. It's going to come back in the presentation. And then we have biofuels, but we don't have a lot of area to grow enough biofuels to fuel what we have. And we have electricity, solar, wind, hydro, etc. Okay. And the nice thing is solar and wind and hydro and geothermal are really our best choices for a sustainable future at the moment, maybe fusion. So here are some clean technologies: our wind, our geothermal, our bio, our hydro. Nuclear is also clean from CO2 emissions. We can get some improvement in smart grids. Carbon capture is going to keep the CO2 out of the air and the climate change down. Green buildings will also help there. So I'm going to call these the solutions of the fuels, but they're not perfect either. Windmills, they're made of carbon fiber. They cannot be recycled. The only thing we can do is throw them in landfill. These are pictures from Wyoming. They're burying them. Europe is going to have 12, in the next 2 or 3 years, they're going to have 12,000 windmills, 36,000 windmill blades. That's 25-year-old windmills. But we've had an exponential growth in windmills in the last 25 years. That 12,000 is going to turn into 100,000 and millions in the next decade that have to be buried. So we're just making large landfills. That's not very environmentally friendly. And then you got solar over here. Look at this beautiful farmland that's been replaced with solar. That's a compromise. You want farmland and agriculture, or even forests, or do you want solar? You've got a choice, because it takes up a lot of land mass. They're not perfect. And then, of course, there's the environmental impact from the manufacturing, the toxics when you create solar panels. Now we're going to get into the big energy picture of what we have. So here is the per capita energy consumption. So this is what each human on Earth consumes in energy. So I just take the total energy consumption in the world and divide by the number of humans. And versus year from 1850 to, well, this goes up to 2007, this particular graph, all right? And what you see here is that over all that time, we've remained at about 11%, 10% renewable energy. It's primarily wood and hydro. I don't see wind in here at all. It's not there, okay, up to about 2007. And all the rest is from non-renewables. So you could say, that all of our standard of living improvements since the 1850s, since you go to someplace like Pioneer Village or Heritage Village in Calgary or someplace like that, and you visit the old West, has been due to non-renewable energy, even in the last 5 years, 10 years, 20 years, right? Now, I updated this graph. Christy actually said, oh, that's only 2007. Yeah, so I updated it. I managed to get data up to about 2014. Data is always delayed a bit that you can get to do these plots. And you'll see that the other renewables and wind is just starting to appear in here. But what's interesting, let me go back. Remember, it was 11% of our total? Because our energy demand went up, it's now 10%. So our net renewables has actually gone down while we've added wind. Interesting. Just 10%. Okay, so how good are we doing at making promises of where we want to go? Well, first we had the Real Summit, the Real Earth Summit. We made a promise in 1992 for 2000 to have certain level of emissions, basically hold approximately constant. We missed it big time. We made a promise at the Kyoto Protocol in 2001, or no, so 2002. Again, what happened? We missed it big time. Oh, well, let's make a promise in 2011 at Copenhagen. No, we missed that big time. Let's move on. Let's make a promise in 2015 for the Paris target. Well, we still have the chance there. The brown line is showing the estimate from the Pan-Canadian Framework on Clean Growth and Climate, where we'll be. The blue line is an estimate if we do nothing. And the green line is showing what we've actually done so far. Okay, so this is a huge challenge. Just to remind you, the purpose of this talk is for you to try to answer the question, what's our biggest energy challenge? Now, I made this plot this weekend. I also made this new plot, and I like the next one. We made another commitment to net zero recently. 2019, we made a commitment to net zero. Let's plot net zero on here. There it is. There's net zero by 2050. Our commitment is actually at a steeper slope and greater decrease in CO2 emissions between the Paris target and 2050, when we go from 2030 to 2035. So that's a huge challenge before us. So what are our options? I'm going to go through these very quickly here. All right. I'm not going to spend details. If you want details, I can come back. Well, we have geothermal. What can we do with geothermal? How much is there? What can you do? Well, ground source heat pumps, I told you, are already part of the solution for home heating, electrical, and there's high grade steam, not available very many places. So there's something called enhanced geothermal energy, which is medium grade thermal energy. There's some pilot plants out in the deep project out in Saskatchewan, for example, on that. And you drill down about 4 to 6 kilometers, very expensive. But you can get these intermediate temperatures, 100 to 120 degrees. Well, what does that mean? Well, look at this particular chart. The box on the right that says high grade steam for power generation, that's what you're going to find in California. You can do that in Yukon, you can do that some in BC. That's great geothermal energy. It's not available in many places. And then look at the red circle on the left. Canadian Shield is like the worst for drilling down. We'll probably have to go down. Well, the record is 6.5 kilometers. If we have to get up to 120 degrees or even 100 degrees in the Canadian Shield, we're down to 8 kilometers or more. That's, and it's exponential cost for this. This is not feasible. All right. So here's a quick map. The west, the orange, the green, and the red are potential areas for geothermal. Out here in Ontario, the rest, most of Canada, not much. Okay, so that's not going to help us. Well, carbon capture, got to get the greenhouse gases down. Let's check carbon capture, right? It's part of the solutions by this Canadian Institute on Climate Choices. Carbon capture is extremely important to those scenarios. Thing is, carbon capture is and is not part of the solution. There are many people arguing today not to give any tax credits to companies to develop carbon capture. They don't want it. They think it is going to create more CO2 emissions, right? That is part of Jevons paradox. They're afraid of Jevons paradox. Will carbon capture actually cause Jevons paradox? There's the fear, right? So just remember Jevons paradox. In terms of Ontario, we have basically 3 major industries that produce most of our CO2 emissions: the refining industry, the cement industry, and the steel industry. And it's mostly down here in southwestern Ontario. Fortunately, the only place to store carbon dioxide in Ontario is in southwestern Ontario in the Cambrian Shield part. And this is where your 20 years comes from, that we answering the questions beginning. But then what? What after the 20 years? What do you do? Well, the government has did this from what? February 17th, so a few days ago. Green steel, that's where you use hydrogen. It's definitely feasible, but you've got to convince companies to get rid of their old technology and replace it with new. It's very similar to saying, oh, you just bought a house for $700,000. And then 1 week later saying, oh, you've got to tear down that house and build a new house that's blue, not green, or sorry, that's green, not blue, for another 700,000. No company's going to do that. They're going to they need to get recoup their investment from what they have there. So there's time delays involved here. But yes, this is a way forward for the steel industry. Cement industry, unfortunately, is going to always create CO2. It's part of the process. That's interesting. Now I got a few other graphs, and then we'll start to wrap this up. Here we have Canada's energy and the economy. Is this an important engineering challenge? Well, this is showing you that they're basically 100% correlated, except something happened in the early 1970s, 1973, 74. And what happened was the oil crisis created a reaction. And it took about a year and a bit for us to react. And what we did is we instituted conservation. And so conservation is a strong part of what we do in energy design today. Right? But what this means is 2 things. A, we had a tool and we applied it, but that tool doesn't exist anymore. And no one knows what tool we can use to disconnect energy from economy at the moment. No one has a secret tool anymore. Secondly, conservation, we're committed to it. We can't go away from it or things will just get worse. What about this graph? This is actually, I tell students, this is the most important graph I'm going to show you. This graph here is what I call the significant use graph. If you take a look at the scientific feasibility, nuclear energy is the clean one. Let's start with nuclear energy. It was discovered, it gets very clean because it was discovered in the late 30s, 40s. So we know when it was discovered, scientific feasibility, right? And then engineering feasibility, we started building nuclear systems, commercial feasibility, early 1960s, utility integration, mid 60s into the 70s, and then significant use. Didn't actually reach 5% around the world. It reached about 3%, but I'm going to call that significant use. All right. That slope there is 40 years. That's a slope of development. That is the fastest any technology has ever developed to deliver large amounts of energy. 40-year time frame there. Remember, the nuclear wasn't just your average commercial venture either. It had the military complex and expenditure behind it. We don't have that type of spending behind our energy transition to sustainable future here. So that slope is very important, 40 years. So if I put it on the graph of our 2050 goal, this is again from this climate choices, Canadian Institute for Climate Choices graph, the 40-year slope actually ends up in 2060, which even makes 2050 look harder to achieve, even if we invest everything in it. Okay. Oh, did I mention that wind and solar are intermittent? That most our electric utilities can only use 20, 25, maybe 30% solar energy and wind energy before they can't handle it without storage. Well, what storage do we have for it? Well, we only have two. There's only two, pumped hydro and compressed air. Both of these are location dependent. Pumped hydro, you need height differences when you need water. Compressed air, you generally, it's not an absolute, but you generally need salt. This is not available in many places, and it isn't available in places. We have it in southwestern Ontario here. They do not have it in Manitoba and Saskatchewan. They have it in Alberta, right? So there's places that have, places that don't. Oh, are you thinking, what about batteries? Oh, I hear batteries, and well, Tesla's out there putting on these big power plants. Sure. But let's take a look at what the science says about large scale. We're not talking just 100 megawatts here, or tens of megawatts and just a gigawatt, or sorry, megawatts power and gigawatt hours. Yeah, batteries can kind of stretch into that category in the upper right, but we want to go far into the upper right. PHS, that's pumped hydro storage. CAES, that's compressed air energy storage. That's our two available technologies. Okay, you can pick hydrogen, but the hydrogen is going to come from natural gas here today. So that's probably not a good choice. And I'll give you. And then the SNG is the synthetic natural gas, which comes from coal. That's probably not a good choice either, unless you have carbon storage, right? So there's really only two. So that's a huge challenge. All right. I'm just looking at the time here. I'll be about 5 minutes just for those keeping the time. I think I started at 17 after, so that's about 45 minutes here. So if we want to develop an energy strategy, and this says national energy strategy because that's what the paper was referring to, but let's assume it's just developing an engineering strategy for whatever project you're working on. This still applies, right? And this comes from a document in 1979, and it still applies. So for example, there's disagreement, even widespread ignorance about some fundamental facts. Well, that's where I gave you the radioactive situation, because we don't know everything, right? And I just wanted to give you a fun one to do. So here are the answers to that particular problem. I love milk, by the way, and it's by far the worst radioactivity wise. But the point is, if you knew the reason, great. But if you don't know, you're ignorant of it, and you can make decisions that are different and not necessarily the best. The reason, by the way, is that radioactive elements tend to be heavy, and the nuclear discharge water allows things to settle out, right? The river water tends to stir it up, so it lifts up the heavy elements. Beer concentrates it. The ocean water has salts and holds them in suspension, and the milk really concentrates them. So once you know the reason, it makes sense. That's the engineering, where you have to take our engineering science, our engineering knowledge, and apply it. And in general, people in the public will not know that, but they'll be making decisions that might affect this. So I gave the radiation example. There's great uncertainty about what the results most commonly suggest that energy policies might produce, right? You suggest something. Well, that's where Jevons paradox comes in. You suggest efficiency. How is it really going to improve it? And then you have, oh, let me just go back here. No easy way to choose between short and long-term objectives. That's called the Faustian bargain. Short-term gains for long-term pain. Fossil fuels today, environmental damage tomorrow is a classic example here. The last one is there's no clear national consensus. There's no consensus. Well, you got carbon tax and carbon cap, right? Or cap and trade. Which one's better? I put down here economic growth for environmental protection. Which one's better? All right. So we have these difficulties. It really all boils down to people first asking, what do they want? And right now we know we want to avoid the impacts of climate change. Okay. Then we have to answer, what can we get? And that's where the engineers and the scientists are going to come in. And we got to answer that question. And so it's not just about us doing the work, which we have to do, or things will be worse, but it's also about informing others so they make good decisions. Right? Just a reminder, here's the Brundtland Report of Sustainable Development. Development meets the needs of the present without compromising the ability of future generations to meet their own needs. This was great because over 100 nations all agreed to it. Everyone agreed to it. I will say that I heard a premier up in Northern Ontario be talking about sustainable development, and all of a sudden he said, I'm in full favor of sustained development. So a bit of a Freudian slip there. If we take a look at legislation in Canada, we have this basic premise of a strategy of sustainable development. It's economic growth provides the conditions in which protection of the environment can best be achieved, and environmental protection balanced with other human goals is necessary to achieve growth that is sustainable. Right? So I just emphasize it's like economic growth tied to the environment so that we sustain the growth. That's what we have. That's our interpretation of the Brundtland Report. I'm going to skip over the design process here and just jump right now to the end of the presentation. So I'm going to return back to the original question. So Santa, hopefully you can post this question again. I'll give a couple of minutes here. If you have any other ideas of what might be the biggest challenge, please place it in the chat now, if that hasn't been done. And Santa's going to pick one or two maybe to add to the answers that you can answer to the biggest energy challenge. All right, so I've given most of my presentation. Maybe you've changed your mind on what the biggest challenge is, or you have something else to add. Please do that in the chat now, and Santa will add that, and we'll do that in a moment. So in general, culture, current development, the way we develop, the way the economy works, our societies work, the cultures we have, the beliefs we have, they're just not sustainable. We need to change that to a sustainable future. And we know they're not sustainable, right? That's why we have to get off gasoline and oil and coal. So the big energy problem is therefore what? All right. Santa, how long might it take us here?
So we're getting a couple answers. I'm just gonna add two. One is from George and one's from Philip, and I'll launch the poll. So
awesome.
Less than 30 seconds.
All right. Now I'm not going to, well, maybe what I'll do is while we're waiting is I'll go back to this design part here, just as a bit of a waiting time while Santa sets that up. So what I put this in here for is when we engineers solve problems, we need to know what the problem is, and then we find a solution. And one of the classic ways of doing this is following the engineering design process. And the most common one first presented to students and the like, there's many, many design processes. I'm not saying this is like the gospel, but this is the most common one here, especially if you have a problem, you have to get it done in a certain time frame. You're going to keep things pretty streamlined and linear. You find the problem and you establish requirements, specifications, constraints, criteria, however you classify them. And from there, you have some ideas and options. And you compare the ideas and options to your specs, and do they meet, and you do some analysis, and you'll go back and forth a bit here between analysis and options, and a lot of cycling here. And I'm not saying that's small work, that can be a huge amount of work there. And then you'll finally decide, because you're going to deliver a product, for example, build it and produce it and deliver what's going to be delivered. So this would be a classic type example of an engineering process. I want to introduce you to a different one. The one I'm going to introduce you can still apply, but it's one that relates to my talk today a little more. And this is the one where it's a cyclic oriented design process. And even the top one was cyclic because I said you go from analysis to options and back and forth. So they're both cyclic. But this one actually says when you have a problem, you initially have some understanding. It could be very little understanding, or it could be a lot, but you have some understanding. And we all know ideas jump to mind. Have you ever heard of someone jumping to a solution? Well, this is called jumping to a solution. And I totally expect it. That's what humans do. You should do it in the design process. What you shouldn't do is jump to a solution and say that is the solution. What you should do next is analyze it, evaluate it, and then that usually changes your understanding. And you can go through this numerous times in a design. But what's interesting about this process is, one, you don't exit when you're finished evaluating and say, I'm finished. It's not a linear exit. You exit with ideas and recommendations. And the last thing I'll say before we enter the poll is what's interesting here is when your understanding changes, the problem changes. And that is what I'm wondering is if that's happened here today already. Given the answers we had at the beginning, given your knowledge, understanding may have changed, did the problem change? And this is the process I actually ran you through a bit today, although very quickly. Normally this would be a multi-week course or something. All right, so we'll see what answers come in. I'm just going to scroll through the answers here.
Yeah, if you'd like, I can read the question.
Yeah, I read them out. Yeah,
okay.
I don't get the poll myself. So.
Oh, okay. All right. So the question is, what is the world's biggest energy challenge? Sorry. And the options are cost, greenhouse gas emission efficiency improvement, emissions and pollution, policy, decision-making, climate change technology, human mindset, innovating photovoltaic solutions for a cleaner world. Biggest challenge is to change people's habits and desire for more.
And desire for which?
For more.
Okay.
So yeah, I'll repeat it again. It's the biggest challenge is to change people's habits and desire for more.
Okay.
And we're getting roughly an even distribution across all options, almost.
No, what I see is I can see the policy one's much higher than the first four.
Yeah. But
And
people definitely voted for all. Yeah.
Okay, so we're getting three big ones.
Mm-hmm.
Human mindset, the habits, and the policy decision. Okay. I think we got 74 of 89. We've got a few people that can't vote here. So why don't we move on to my next slide?
Would you like me to end the poll?
Yes, end the poll.
Okay.
And we'll just take a look at the results. I think we know what the three are. But is it almost ended or? There we go. Okay, so the three largest answers, about 25, let's say 1/4 each, policy decision-making, human mindset, and to change people's habits, and I can't read the rest. But let's just say to change people's habits. All right, so let me share my screen again. And let me move the slide forward. So my answer to this actually changed several times over the last 30 years of researching energy. But the one I've come up to, and it's not one I actually stated explicitly in the presentation, but I would say that the last answer that was provided It would be the closest. So I would answer, it's the concept of growth is essentially a belief. People believe things must grow. You'd be amazed at the resistance you get if you talk about things remaining constant. Just think about the growth of the economy, right? And I realize the economy hopefully can be disconnected from energy, but at the moment it can't. But if our economic thought is that we always must have a growth rate, and we usually think of a growth rate below 1% as being bad for the economy. A growth rate of 2.5% is excellent, right? Around 2 or a little less than 2 is sort of a nice, healthy growth rate for the economy. But it's a growth rate. And you know a growth rate that's constant each year as an engineer is an exponential function. And if we are going to believe that the economy must grow and we cannot find a way to disconnect energy from the economy, our energy situation is going to be very, very difficult. I'm going to give one example of exponential growth. I didn't put a slide in for this, but I'll just give the example, and this is where we'll end the presentation. If you actually take an exponential function, all right, and you imagine how much, by the way, I think it's on the graphs. Let me just go back. I may not have it on the graph. I'm just thinking I may. If I don't know if I put the number on there. If it's not there, I'll tell you the number. It's not there. Okay. If I was to multiply the population by the energy here, you actually get a growth rate of about 2.5% per year. That's been the growth rate of energy in the world since 1850, 2.5% per year. That translates into approximately a doubling time of about 24, 25 years. That means it's like compound interest. If I have $100 in the bank and I have a 2.5% interest rate, annual interest rate, I will have $200 in the bank in 25 years. It's doubled. Well, for energy, 25 years is about one generation, right? What that means is that since 2000 or 1995 till now, approximately, we're using twice as much energy in the world. Between now and 2050, which is about 25 years, okay, 28, but that's about 25, we're going to use twice as much energy as we use today. So not only do we have to find a substitution for this huge amount, we have to find a substitution for twice this amount in that time period. Now, I'm going to give you another characteristic of an exponential function. The amount of energy from 1995 on an exponential function, if I integrate that exponential, nice that you're engineers so I can talk about integration. If I integrate that exponential function from 1995 back to minus infinity, back to the time of the dinosaurs, right? Just the exponential function. You know how much energy was consumed in that time? The same energy consumed between 95 and 2020. So that means that between now and 2050, we will consume the same amount of energy that we have consumed since the beginning of human civilization. Now, it's not 100% true because things level off, but you get the basic idea. Exponential growth is really, really strong. All the energy that we consume between now and 2050 is going to be equal to everything we've already consumed since we ever discovered oil and coal. So when you start thinking that that energy we consumed in all that previous time is causing all this huge environmental impact, what are we going to do in the next 25 years if we don't change this? It's scary. But we can do it. And I'd be glad to answer any questions at this point. So I'm going to flip to my last slide. Sorry, I think I went a little over there, but the end. There we go. So,
Thanks, Roydon. So we'll have a question and answer section following the presentation, and Maria will be the person to master the question and answer session.
Sure, thank you, Christy. Thank you, Dr. Fraser. We have a couple of questions here on the slide though, so I start reading the first one. The question is that, what are your thoughts on nuclear fusion energy generation?
On nuclear fusion?
Yes.
Well, first off, yeah. So first thing on nuclear fusion, I had a choice in grad school of going to the University of Toronto to study fusion or going, I ended up studying engines down in the States. I was a little concerned at the time that it might not be a future career for me. So that's why I didn't do it. And that was back in 1983. It's an engineering challenge. They had a tokamak reactor. I went to Princeton. They had a tokamak reactor in Princeton, actually, the only one in North America. And I talked to a lot of physics people working on that device, and they were engineering challenges. They were not scientific challenges. There were really a lot of engineering. And you heard talk at the time in 1983, oh, by 2000 we'll have it. You now hear talk around 2050, we might have it. There have been certainly some we've hit the breakthrough. Fusion energy is interesting in that if we do achieve it, I think we will. It will happen. It's just going to take longer than we initially planned. It becomes, I didn't present the slides here, but you think about, well, let me go, think of the slide that I showed, the per capita energy consumption, where we used non-renewable fuel since about 1850. That is a major part of the Industrial Revolution. And it's because energy became easily and cheaply available. So if you bring on fusion, energy is going to be, much more energy is going to be easily, and I assume cheaply available. Okay, eventually being cheaply. You put bacteria in a petri dish that's energy filled, they grow exponentially. If the economy is tied to energy, the economy is going to grow exponentially. The economy needs resources. Those resources are going to come from the environment. So if you want my prediction, fusion energy is going to hurt the environment. If you want, that's the short answer.
Thank you. The next question is that, what technologies do you think should get more focus? Which ones less?
Oh, no suggestions. Which one should get more focus? Energy storage, number one. Large scale energy storage for wind. The quickest way, we have technology for wind, and we know we can do it, we can produce it. If I looked at the slope and go back to my significant use graph, I had wind on it, it could get down to significant use by 2040 and into 2050. But the only way wind is going to be a significant energy source is with energy storage. So I would say that's number one. That changes the whole equation of what we can do.
All right. So the next question is that, what are your thoughts on driverless vehicles' potential to save energy?
Of electric vehicles to save energy?
Yes.
Yes. Oh, they're great. My next car, I'm sure, is going to be an electrified vehicle. Now, I'm not going to say it's going to be a pure electric vehicle. It could be a range extended electric vehicle, which might have a small engine on it, but it's going to be highly electrified. And the reason for that is overall, it can have a much lower, it's the only way to get a low environmental impact from vehicles. It's virtually the only way. I mean, you can have compressed air cars. They're not going to have huge range. You could certainly produce hydrogen fuel cells. So those are going to be big too. But hydrogen fuel cells are what? They're electrified vehicles. And so I would have a plug-in fuel cell vehicle, and my range extender would be a fuel cell. So it's the way to go. It's the only way to go that I see is electrified vehicles.
Sorry to interrupt. The question was actually autonomous and driverless vehicle, not electric.
Okay.
Just wanted to point out.
Okay. So with autonomous vehicles, that's fine. The future autonomous vehicles, they're semi-autonomous are here. it's the future. We're going to live with the problems, like, there's going to be accidents and safety problems with them. And we will become accustomed to it. Just remember this. We used to drive cars on the road in the 60s, and the death rates were 10 times the death rates on the road today. We had no problem driving with those huge death rates. We adapt. All right. I'm not saying there's going to be death rates with autonomous. There's probably going to be a lot less, but there's going to be ones that you really are going to question. There's going to be some ethical ones that are really going to cause questions. Do you have a computer save the person in the car or save the person that's on the road, standing by the road? How do you make that choice? Does it matter if it's an old person in the car and a young person on the road and vice versa? How do you make that choice? When do you switch choices? I think that's the type of thing we're going to run into. And then you're going to see a lot of court cases around, you could have programmed it this way, but you programmed it that way. Right? But safety-wise, I expect it to be a lot safer. Cars are a lot safer today with semi-autonomous features. So I expect it to be safer in the future.
Excuse me, I'm the one that put the question. I was more interested on your thoughts on autonomous vehicles on energy consumption.
Oh, okay. Yeah, sorry about that.
Don't want to talk about the trolley problem. We already talked about that too much.
No, okay, that's fine. That's fine. No, it's going to improve it's an efficiency improvement. It's especially with the vehicle to infrastructure, which means vehicle to vehicle and vehicle to traffic lights. So for example, your car might actually speed up for a traffic light to make it through a red so it doesn't have to stop and idle, or at least not have that acceleration. Even if it's an electric car, not having that acceleration from stop to go still saves some energy. You might find your car slows down for a stoplight just by communication. You'll find that instead of having these accordion actions on the road, that when you drive the 401 in heavy traffic, it's a nice steady stream. It'll be more efficient. It's going to improve efficiency. The only concern is Jevons paradox from an efficiency perspective.
Right. So the next question is that, are there any failed technologies that you think should have been explored further?
Any technologies that should have been explored further?
Any failed technologies
Failed.
that you think should have been explored further?
I don't know about failed. I know, like I said, like compressed air energy storage isn't a failed technology. There's 2 of them in the world, but they were built like 25, 30 years, 40 years ago, actually, right? And there's been nothing since. So it's not exactly failed. It's just failed to take off. And right, people just have not used it. Nothing comes to mind where I'd say the technology was sort of neglected for some reason. If someone has something in mind, I'd be glad to, if I know about it, I'll talk about it. If I don't, I'll probably look it up because I'll be interested.
Thanks, Dr. Roydon. I think we have to move on to the next session. If you have more questions, there will be an open session for like any upcoming questions at the end of the seminar. So thanks, Roydon. And I will introduce Ashley to be our today's thanker for our participants and speakers. To Ashley.
Thank you very much, Christy. Tonight, I have the honor of thanking everyone that made this seminar possible. And to start off, I of course have to thank Dr. Roydon Fraser for providing such a thought-provoking presentation regarding the engineer's perspective of the climate change energy situation. Your extensive knowledge and passion on the topic was expressed throughout your presentation, and I know I'm not the only one that will be thinking of these topics with a different lens after this. I would like to extend my appreciation and thanks to all our co-sponsors for this event. This includes the PEO Ottawa Chapter as the lead chapter this evening, PEO York Chapter, PEO West Toronto Chapter, PEO East Toronto Chapter, PEO Scarborough Chapter, PEO London Chapter, TECS Toastmaster Group, the SCORE Toastmaster Group, the Society of Women Engineers Ottawa, and IEEE Peterborough Chapter. I would like to give a big thanks to Christy and Jim, who were the organizers of this evening's event. Thank you for all the time that you guys have dedicated to organizing this and other seminars for the purposes of bringing awareness and educating people on the critical climate change topics. I would also like to thank the team of volunteers that are part of this evening's event, including, but not limited to, Sana, Marcel, me, P.Eng, Maria, Christopher, and Hanan. And of course, I'd like to thank everyone that has attended this seminar tonight. It is through your continued support that has enabled the Climate Action Group to organize and host events like tonight, spotlighting the important topics relating to climate change. Thank you very much, everyone. Next up, I'd like to invite Christopher to provide the concluding remarks for this evening's presentation. Thank you.
Thank you, Ashley, and well said. And once again, thank you, Dr. Fraser, and presentation well done. Today, we've learned a lot about energy and choices from the detailed insights of Dr. Fraser. It's very important to make informed decisions in life, in our careers, and with the new information today, it's important as engineers, as professionals, as Canadians, and as humans to do something with that information. When I'm inspired or I get some really interesting information, I always ask myself one question. If I was in a position of power to do whatever it is possible, what would I do with this information? What would I do with this new knowledge? There's an old saying, give a person unlimited power and watch what they do with it, and it will reveal their true character. And today I would encourage all those watching to ask yourselves, what will you do with this knowledge? Because climate change is here. Climate change is now, and the future depends on what we do today. I would like to remind everyone that there's an additional networking time and an additional Q&A in just a few minutes. So stay online and we welcome you. And thank you again, Dr. Fraser. I'll pass this on over to Councillor Jim Chisel for final remarks.
Thanks a lot, Christopher. I'd like to thank the volunteers as well. And in particular, I'd like to point out the role of Christy. Just phenomenal organizer and did just a fantastic job organizing this. So thank you. Thank you, Christy. And of course, Dr. Fraser, an important talk, and especially at the end, the profound conclusion that we need to separate energy from growth. And I know other people are talking about that. And I know a professor, Peter Victor at York University, has written a recent book on that whole topic. And the Climate Change Group will be considering that book in particular and the topic. So hopefully one of our future seminars will deal with that very, very important issue. If you're interested in being involved in the Climate Change Group, there will be a survey that will go out at the end of this meeting. And one of the options will be for you to put your email for future contact. The Climate Change Group is an unofficial group of people from the PEO, and our objective is to talk about climate change, to make it better understood, to make it an important topic within chapters, within the PEO, with a view that it gets on the radar of the PEO more, and that it actually gets addressed through a strategic plan of the PEO. So if you're interested in working on that, do fill in the survey and give your email address. So as Christopher mentioned, the meeting will now be adjourned, but stick around if you want to have some informal networking. So meeting adjourned at this point.
Thank you, Jim, and thank you to Dr. Roydon Fraser. I don't know why I just stopped for a second. Roydon Fraser. Thank you so much. We really appreciate it. And now on to the networking part, or the networking session. So thanks to everybody that stayed on the call. We appreciate it. I guess you're here to network as well. So we're open not just to networking, but we're also open to questions that you may have that you'd like answered. Feel free to go off mute and just say whatever question you have, or introduce yourself and network with everybody. Feel free to thank our speaker as well. So yeah, we're open to everything. And we have a question prepared by P.Eng. P.Eng, whenever you're ready, go off mute and share that burning question that you have.
I've been having the question since I heard there's a seminar related to climate change from an engineer's perspective. So Dr. Fraser, thank you so much for the presentation. I had a background in, I guess, electrical load shedding and simulation for water heaters. I'm just wondering, like, I spent 3 years doing my master's, figure out all the kind of intelligent algorithms to do this kind of load control for small loads like water heaters. Now I look at the bigger picture, I start to think, is it meaningful to do such research, or should we focus on bigger picture? I know sometimes, devil is in the details, but sometimes I feel like for research like what I did before at my master's program, now I look at it, I go, is it even meaningful, or is that going to make a big enough impact?
My short answer is it's meaningful. How big of impact it makes, I'm not quite sure.
Mhm.
To tackle the problem, it's not just the big picture. The big picture is what you got to be aware of, but the solutions are going to be close to home. It's going to be distributed solutions. And what you're describing as your research is a distributed solution.
Exactly.
And you have to have that, and you have to have options. You can't go into every home and say you're all going to get heat pumps. It's not going to work. You've got to give them other options. The options might, or heat pumps of a certain type. What quite often happens when you have these big scale ideas is uniform approaches come forward, and you have to adopt to people's different economic situations, different housing situations, different just viewpoints to the world of what's important to them. And people are going to experiment. So what you worked on may end up, maybe something better will come along in terms of how to do the intelligent control of the hot water systems, right? But you have to do it. If you can't have one solution, you will find that you'll have major problems. So I'd say it's very valuable. We have students here working on small systems, and they each make, some of them make an improvement, some of them say don't do it, but that's still important knowledge.
Thank you.
Somebody mentioned a survey at the end. When are you going to email this to us, or what?
Yes, at the end of this meeting, probably tonight, there will be a survey that goes out. I know people have asked if this will be posted as well, this presentation. And I will ask the West Toronto chapter for sure to post it. And Sana, you're here as well. Maybe you can comment whether the Ottawa chapter could post it. And you can access the chapter website through the PEO website. So you go to the PEO website, and almost for sure the West Toronto chapter will post it. And hopefully the Ottawa chapter will post it as well.
Okay, thank you.
The answer is yes, we will post it.
So those members who couldn't attend tonight, so could we share these slides with them, or what do you want me from London chapters to do? Or should we just reference the link to your chapter, or what?
Roydon, do you have any objection to sharing your slides? So we can
No, I put references on all the slides that needed references, so I can share them, right? So it's just fair use of these different information, so that's fine.
Okay, so I will ask the West Toronto chapter to not just post the video, but also the slides, and hopefully Ottawa could do that as well.
Yeah. The only thing I'd ask is if anyone uses them, make sure proper credit's given to whatever slides are.
Okay, thank you.
Great, thank you so much. Anybody else with any question, or before I ask an icebreaker question?
No,
there's a question in the chat box.
Jim, would you like me to read the question out loud, or would you like to do that?
Please go ahead.
Okay, so question from Jim. The world has abundant but not unlimited basic natural materials and resources. With unlimited growth, are we eventually going to reach the resource limit?
Sure. Oh, boy.
For sure. But we might meet the environmental damage limit first.
Good point. Good point. Yeah.
Yeah.
There has been a study of this actually that I saw a report by, I can't remember his name, that looked at this. And for example, take lithium. It's a fairly scarce resource. If we're going to have electric vehicles, we may eventually not have enough lithium to, or we're going to have to find another material for batteries.
Yeah. There's maybe a little story I'd tell you. It's about Julian Simon and Paul Ehrlich. This is back in the Reagan years. Julian Simon was Reagan's economic advisor. Paul Ehrlich was the author of The Population Bomb. I forget if that's late 60s, early 70s. He wrote the book with his wife. They had an argument about scarcity of resources, and they have a bet. And Julian Simon said there's no such thing as scarcity. That's the economics person. And that's really what this question is about, scarcity. There's no such thing as scarcity. And at the time, copper was becoming, apparently looking like it was becoming scarce and expensive, right? So the bet was that Julian Simon had asked Paul Ehrlich to pick 10 commodities, and I don't know if it was on NASDAQ, but 10 commodities that would increase in price, because you know the old supply-demand argument in economics, that would increase in price in a couple of years. I can't remember the exact results, but it's something like 8 out of 10 decreased in price. And the two that increased in price increased very little, and copper decreased in price, which was the one that started the whole consideration. And eventually we may have found a substitute for copper. It was microwaves, right? So the argument of substitution, if you talk to economists, if you believe that there's sort of this empirical correlation that scientists and engineers have always found substitutes. On the battery side, for large scale energy storage, they're not talking lithium, they're talking iron air batteries, which would be very, very large. But something we don't see around today, but maybe in the future. Right? So anyway, just a little story about scarcity. Some economists will say there's no such thing.
Great. We have another question coming in. It's a question from Edward. Why do we not see more implementations such as Drake Landing in Alberta? Oh. Sorry, it's, can you still hear me?
Yes.
Okay, sorry, it just completely closed the whole window for me. So yeah, such as Drake Landing in Alberta, it is a solar thermal. Hello?
I think Edward was maybe wanting to ask the question. I think he came on the screen for a sec.
Okay.
Yeah, it's Edward here. Yeah, just as the question states, there's a community along the lines of green building. There's a community in Alberta called Drake Landing. Been around for, I think, at least 10 years. Mm-hmm. They use solar thermal panels, and basically in a nearby park or field, they have a geothermal seasonal storage set up. Apparently, in terms of winter energy demand, based on what they collect, they can meet 80–90% of winter heating requirements. Again, that houses, I think, are more efficient than usual. Most of them are built to the R2000 standard. But we don't see many communities built like this. Is it a cost issue? Do you have any idea?
Yeah, I'm quite familiar with Drake Landing and the thermal storage. I call that a geothermal battery is essentially what they have. And it's an excellent example. Cost. It's not that it's extremely costly. It's just
The cost, okay.
So I'm going to
Yeah.
give you I'm going to give you another question, a quiz to everybody here. All right, you have $10,000. Well, no, let's I got to be realistic with house prices today. You have an extra $50,000. All right, and you have a choice for it. You're building a new house because essentially for a community like Drake's Landing, you have to design it from the bottom up for it to be reasonably economical, right? Or at least the cheapest. So you have $50,000 available. You have a choice. You can install high efficiency systems in your house. That means increase the insulation in your house, put in heat recovery on your showers, just put in all these systems for 50,000. Or you can have an extra room. You can have a study room or an extra bedroom in your house. Which one are you going to build?
Ed here, I would go for the energy efficiency measures.
Yeah.
But
what do you think the average person is going to answer?
yeah, I think probably the granite countertops and the extra space.
Especially if they don't know they're going to live there a long time. Let's say they think, oh, I might only be here 5 years, and the payback might be 15 or 20 years.
Right.
It's that type of argument too. So it's not just its cost, it's also this decision of short versus long term. And
do you think PACE based schemes may provide opportunities to move the costs or keep it with the house as opposed to individuals?
I think there's schemes that can do that. Sure.
Right. Okay.
Yeah. But it takes a bit of a change. Well, let's think about building codes today and what you can do regulation wise. We don't even require R2000 houses yet today. Think about that. That's 20 years ago.
Yeah.
Well, actually, yeah. R2000 was developed in the 1990s, right? We don't even require that today because it costs.
Right. Yeah. Yeah.
So Drake Landing it's great, but it's just an example of extra insulation or R2000. Why don't those exist?
Yeah. I think they're looking to improve the building code by 2030.
Yeah. So
to net zero.
So regulation could have a large effect on things like, these geothermal batteries.
Yeah.
Yeah.
All right. Thank you very much.
All right, so apologies. Yeah, go ahead.
Dr. Fraser, you showed an interesting slide earlier about hydrogen versus gasoline and the safety of it and the practicality of it. What are your thoughts on future energy in terms of hydrogen? Would you say that would be a key player in future energy?
Absolutely. Absolutely. Hydrogen's a necessity. It's a necessity, and you can't just run everything on electricity.
Yeah.
Hydrogen, it's, I don't know, it's a short way of saying we will have hydrogen in the future. Some industrial processes are going to need hydrogen. They can't use electricity per se. It's a great, and it's not necessarily going to be hydrogen. It may be ammonia, which is a way to store hydrogen.
Yeah, storing it.
Right. So if I wanted to, so for example, I'll give an example. If I wanted to get the solar energy from Brazil to Europe, how am I going to transport it? A big underlying wire cable? No way. Electricity is not going to do it. Right. The only way I'm going to get all that is I'm going to put it into hydrogen to get the energy from Brazil to, right, where, let's say that, and then say the Sahara Desert, let's say we have solar panels across the Sahara Desert, right, where the sun exists and we want to move it. So the transportation of energy along wires is not fantastic because resistance eventually kills you over long distances. But if you can put it into a medium like hydrogen and transport it, so that's what it is going to be part of the situation. Now, when it comes about, that's going to chicken and egg thing. Do you have the devices first or the technology? It's going to be gradual to get there. Electricity is here today, so that's why it's a little, we're going to see it first.
Yeah. Thank you very much.
Hi, Jim again. I posted another comment. We focused on mitigation of greenhouse gases and other emissions. Climate change is also going to need engineers to adapt to the change in climate when designing and building new infrastructure and strengthening existing assets. I think that's a very important area for the engineering perspective as well.
It's extremely important. And I would say it's extremely important for the building codes to start. They got to realize how things are going to change in their local climate. You just go up north and you're going to start losing the permafrost.
They are revising the Ontario building code at the moment, or consultation on.
Yeah. But it's going to take a lot of vision and a little bit of luck to get it right, because you're going to make changes that have to apply 50 years down the line when things could be dramatically different in terms of the energy flows and the local weather, and that has to be exposed, things exposed to. Right? I guess today the big thing we see is flooding. Flooding patterns changing or getting worse.
Dr. Fraser?
Yes.
I have maybe a two-part question, but also amazing presentation, by the way. I really enjoyed this. So my first question is regarding the hydrogen electrolysis you mentioned earlier. Why has its widespread use met resistance? What do you think is holding it back? And and the second part is, have you heard of liquid metal bubble reactors for producing hydrogen from methane gas?
Okay, so I'll do the reactor ones first. I've heard of them, but I don't know them well, so I can't really comment on that. Now since you've asked the question, it's just like when a student asks me a question, I go and learn it. So I'm going to have to go learn that one. The electrolyzers, it's a cost issue, cost efficiency issue. That's what it boils down to. It's a lot cheaper to make hydrogen from natural gas than from electrolysis. Just for on a good side of it, we actually have at least two very strong electrolysis companies in Ontario. So electrolysis might be a good thing for us. And we have Hydrogenics, which I guess is now Cummins. So that's a US company, but it's in Mississauga. They have electrolyzer technology, and no doubt we'll be using that. And they're moving towards hydrogen for their diesel vehicles. And then you have a company, I can't remember the name, unfortunately. I wish I could plug the name, but there's a company up here, and I think it's Owen Sound, where they have technology also to produce hydrogen from electrolysis, and I hope both those companies do well with that. It is the way we want to produce it. Just another problem with electrolysis is if you're thinking you're going to use solar and wind, you really want an electrolysis process to run continuously. You don't want to keep shutting it off. And wind energy, by the way, goes up and down a lot. Like even in 5 seconds, it can change a lot, like gusty and that. So you want to be able to balance the energy out. So you need some sort of buffer and storage. And then that'll also help electrolysis to work.
Okay, that's a great explanation. And the intermittent nature of the hydrogen supply ties into the other part. In my graduation project, we designed a liquid metal bubble reactor, and being able to have an industrial constant supply of hydrogen required the design of this reactor that could just convert methane into hydrogen and solid carbon. And I guess that the design challenge is to remove this solid carbon in ever increasing purity, and to make more useful, more high value carbon products such as nanotubes if you have the right catalyst. Traditionally it could come out as maybe road filler or something, but yeah, it was initially the initial reactor to another main reactor that would reuse that hydrogen and directly hydrogenate CO2 to form DME, and DME was the alternative energy that we were producing for the project. So But thank you so much for your presentation, and the larger scale picture is something that I greatly appreciate.
Could I ask you a favor, Eric? Could you send me, just that, like I said, I'm going to look it up, but if you just send me some initial information to get me directed in the right direction toward this technology you're talking about, that'd be great.
Absolutely.
Thanks.
I'm going to jump in with a very controversial question. Of course, there is a consensus on greenhouse gases, but there are a few scientists who have an opposite view. And as engineers, are we kidding ourselves that we're forecasting what the climate will be like in 50 years? There's other things affecting climate, and there are other points of view on this. For example, one point of view is that carbon emissions in the atmosphere will reach a saturation level. In other words, it's not a linear relationship between carbon content in the atmosphere and temperature. Anybody have any thoughts on this? I mean, as engineers, we should make sure that we're not trying to solve a problem that maybe is not going to exist in 50 years' time.
I can certainly comment, but does anyone else want to comment first? Okay, I'll take it away first, and someone else may want to comment. Totally correct. You don't want to solve a problem that in 50 years' time is not a problem. The saturation issue is an issue, and the saturation issue, if you're not familiar with, is that it's really that you have a blanket around the planet. I don't have these slides here to show you this, but the blanket, it basically reflects back infrared radiation. And once you reflect back most of the infrared radiation, and you have essentially, it's not really conduction, but let's call it conduction out of this blanket, it's going to reach a steady state. And if the blanket no longer lets any CO2 through and it all bounces back, it's not going to matter. So you are going to have a decreasing effect. I have not seen any good work to say we're near that saturation point. But I have, I mean, I guess I've seen results that say we're getting close. But the bigger concern, I'm going to say, is not CO2. I'm going to put natural gas out there, methane. Methane's nowhere near its saturation in terms of its wavelengths that it absorbs. And we have huge methane sources coming. In particular, the permafrost starts melting, and they're going to get a huge release of hydrocarbons. Those hydrocarbons, in fact, to the point that it might be at the point now that if we stopped all CO2 production, man-made CO2 production, with the warming that's going to occur with the CO2 we have in the atmosphere already, which has about a 100-year lifetime, by the way. So there's a huge lag for us to recover from anything we put up there. We might get more greenhouse gases in the form of methane from the permafrost area than in greenhouse effect than anything we emit as humans. So there's these effects. Now, what I'm going to comment on is I did mention those films at the beginning. You can get the counter arguments for. I'll just make two points. One's Le Chatelet's principle, something most people learn in first year chemistry. Yeah. So first year chemistry, Le Chatelet's principle, I think we get a little echo there, but applies to first year chemistry. Le Chatelet's principle applies to chemical systems, but really applies to chemical systems or thermodynamic system, applies to complex thermodynamic systems, and essentially says thermodynamic systems, certain systems will resist change. So it is true, you can do certain changes and other things won't change a lot because the system resists this, okay? It can also be you hit an unstable point. An unstable point, you get a flip, Lake Erie flips, for example. It'll go from an algae dominated to environment, and it'll flip and it'll be healthy and for fish to live in, and then it'll flip to algae again and not be healthy for fish. So it flips. So you can get either these quick flips You can get these slow growths, or you can get these compensating effects. And it's a complex system. We don't know which ones are going to win out. And this goes back to the idea of changing building codes. Do you actually know what's going to happen? It's going to be tough, is what I'm going to say. The one thing I will say with regard to global warming in terms of the argument, so not the question of saturation and whether we reached the saturation, but I guess there's 2 points here. The oceans are not saturated yet. And there's going to be a lot of damage in the ocean to life in the ocean by increased CO2, even if we are saturated by the atmosphere, global warming. The second thing is that when it comes to carbon dioxide, I'm just trying to think, I just lost my second thought there. Okay, if it comes back to me, I'll think of it, but there's a lot of uncertainty. And remember, I put those 4 points up about how you make policy for this future. It's difficult. It's difficult.
Thanks,
Thank you so
Dr.
much.
Ryerson. Yeah.
If you want to go ahead, Christy, I was
I
just
think
gonna.
Dr. Roydon has already answered so many questions. And
Yes.
if you have any upcoming question, you're welcome to type a question in the survey after the seminar. And if you have like suggestions for the future related topics, we're welcome to know. And the presentation slides will be shared to those people who leave their email address in the survey. We all appreciate your participation in today's seminar, and I will give a big thank to Dr. Roydon Fraser and all the team members who have been our co-sponsors, volunteer, and teammates. You are doing an amazing job today. I think we have to end the meeting. It has already delayed for over 20 minutes. So we are looking forward to seeing you in the upcoming seminar. I think Christopher have another one at March 4th or 3rd. Christopher, do you want to introduce a little bit?
Yeah, absolutely. So March 3rd, which is just next Thursday, I'll be continuing the climate change conversation, similar to Roydon's topics, but of course, I'll be focusing on some solutions and some different perspectives. I'll be talking about applying a strategic process solution to address climate change. So I'll be going into a lot of details. It'll be a technical seminar. So I do wish to invite you. The registration link is just in the chat there, and I hope to see you there. Thanks.
Thanks, Christopher. I'll share the link for your seminar again. Please click the link for free tickets. And thank you for all your participation. And back to you, Senna, for closing remarks.
Yeah, thank you so much, everyone, for participating. On behalf of the Ottawa chapter and all the chapters who are participating today, we're so grateful to have you. Please do come back for more webinars and seminars. Thank you again to Professor Roydon. We appreciate your time and effort, and we definitely did learn a lot. I mean, I took a lot of notes. I'm sure a lot of us have. We appreciate you, and congratulations again on the elections. And with that, I'll tell you all to have a wonderful evening and to rest well. And until next time, take care, everyone.
Thank you.
Good night, everyone.
Thank you very much. Thanks, Christy. Thanks, Anna, Christopher, everyone that helped out here. Great. I mean, you're all great. Thank you.
Thank you.
Thanks a lot.
Take care.
Bye-bye.
Bye.
Yeah.